Hello, this is next lecture, lecture number 3 for Math 609. In this lecture, we will continue with the LU factorization of a matrix. Last time we showed that if we have a matrix A, and if during the process of Gauss elimination, all pivot elements A, K, K are different from 0, then we can represent the matrix A as a product of two matrices, a matrix L, which is a lower triangular matrix, which we obtain during the process of Gauss elimination. We assemble this matrix with the information from that we obtained during the Gauss elimination, and the matrix U, which is the resulting matrix of Gauss elimination. What we will discuss today, or part of what we'll discuss today, will be what is happening if one or more of these pivot elements are equal to 0. And in order to do that, we will start with the definition of a permutation matrix. So a permutation matrix P is a square matrix that is obtained from the same size identity matrix by permutation of the rows of the identity matrix. Such a matrix is always row equivalent to the identity matrix. So if, for example, we start with a 3 by 3 identity matrix, because it is less writing, 1 0 0 0 1 0 0 0 1, and we can create a permutation matrix from this matrix by permuting the rows. Let's say the last row is on first position, the first row is on second position, and the second row is on third position. So this permutation matrix, let's see how we got it from the identity. On first place, we put row 3. On second place, we put row 1. And on last place, we put row 2. And if we look column-wise, so here we put column 2. Here we put column 3. And here we put column 1. So now let's see what will happen if I have a matrix A, A11, A12, A13, A21, A22, A23, and A31, A32, A33. And if we multiply this matrix by this particular, so this is the matrix A, if we multiply it by this particular matrix P, 0, 0, 1, 1, 0, 0, and 0, 1, 0. If we do the multiplication, we will see here that on the first row will be actually the third row. So we'll have A31, A32, A33, because when you multiply this row by all the columns, we'll pull out the row number 3 to be on the first position. Then we'll have row number 1, A11, A12, A13. And then we will have row number 2, A21, A22, and A23. So what is happening here, we see that this is row 3 of the original matrix. Here is row 1 of the original matrix, and here is row 2 of the original matrix. If we compare these labels here with this label here, then the observation is the following. If I have a matrix A and multiply it on the left by a permutation matrix, I end up with a matrix that is obtained from the matrix A after moving or permuting the rows of the matrix A according to the rule that was used to create the matrix P from the identity matrix. So to create the matrix P from the identity matrix, I put row 3 on first place, row 1 on second place, and row 2 on third place. This is how I'm going to create the product of these two matrices. I put row 3 of the matrix A on first place, row 1 of the matrix A on second place, and row 2 of the matrix A on the third place. And if I multiply the matrix A on the left, on the right by the same permutation matrix, 0, 1, 0, then what will be this result here? The result will be a matrix, and this matrix will be this obtained from the original matrix by putting column 2 of the matrix A on first position, and then column 3, it will be exactly following the rule that I obtained the matrix P from the identity. I obtained the matrix P from the identity by putting column 2 of the identity first, column 3 of the identity second, and column 1 of the identity on the third place. And here I put, if you do the multiplication, you will see that it is the same as putting the second column of A on the first place and the third column of A1, 3, and then we will have A2, 3, and A3, 3, and then this is column 3, and then at the end we'll have column 1, A1, 1, A2, 1, and A3, 1. So we illustrated those two properties of the permutation matrix. That the first property here states that left multiplication by a permutation matrix, and this is here the left permutation multiplication by a permutation matrix, it rearranges the corresponding rows. And in which way? We saw in that the rule of the rearrangement follows the rule of rearrangement of the permutation matrix, namely how the permutation matrix was obtained from the identity. And right multiplication by a permutation matrix rearranges the corresponding columns. In which way? They follow the rule of the same rearrangement as the rearrangement of the permutation matrix from the identity. So if the permutation matrix is obtained from the identity following a particular rearrangement, then the product will be obtained from the original matrix following the same rearrangement. A product of permutation matrices is again a permutation matrix. And if we take the inverse of a permutation matrix, this is the same matrix, but the transpose of the same matrix. So this is P inverse is equal to P transpose. So last time we discussed that there were some matrices for which if we want to do Gauss elimination, we could not. And if we wanted to represent this matrix as a product of a lower triangular and upper triangular, we could not. And we could not follow the Gauss elimination because this pivot element here, it was equal to 0. However, so let's recall that this was the matrix A, the 2 by 2 matrix, 0, 1, 1, 1. And if we look at this matrix, and if we multiply this matrix by this permutation matrix, so what is the permutation matrix? On first position, I put row 2 of the identity, and on this position is row 1 of the identity. When I multiply P times A, the resulting matrix is the matrix where first is row 2, and then the second one will be row 1. And then this matrix now does have an LU factorization, and therefore we see that for the matrix L did not have an LU factorization, but if I permute the rows in a matrix A, I will end up with a matrix PA, and then this matrix PA has an LU factorization. And in general, this holds for a general matrix A. Given a matrix A, there is a permutation matrix P such that P times A is equal to L times U. This holds for a general matrix A. What we will discuss here, since we are talking about solving linear systems, we will discuss this for matrices A, which are invertible. Namely, the determinant of the matrix A is different from 0. Remember that when we were doing the Gauss elimination, and now we'll go back to the Gauss elimination. Eventually, at step K, we end up with this matrix. And in this matrix, AKK is the pivot element. And this is column K, and this is row K. So the pivot element stays on the kth column and on the kth row. And if it happens that this element here is 0, because with our discussion, we wanted this element to be non-zero so that we can compute the corresponding L's and therefore make all these blue elements equal to 0 by adding to the rows containing a blue element the row containing the red element multiplied by a certain number. So if it happens that the element AKKK is equal to 0, then what we want to do is we would like to exchange the kth row with some of the rows that are below, let's say with row I, that are below. And note that it is important to remember that the index I is always bigger than K because the row I is below K. So I is among the numbers K plus 1 up to M, and therefore I is strictly bigger than K. So we would like to exchange this row with some of the rows below. Which one? We will discuss exactly how we are choosing the row with which we want to exchange row K. The question is, could it happen that none of those rows is could be exchanged? What does that mean? Could it happen that all the blue elements here, all the blue entries of the matrix are equal to 0? So we know that AKK is equal to 0. Can it happen that all the blue elements, namely all JKK, are equal to 0 for J equal K plus 1 and so on? So all these elements equal to 0, and then we cannot exchange anything because we don't have to where to choose from. Well, the answer to this question is no, it cannot happen. So if AKK is 0, then at least one of those blue elements will be non-zero. Why? Because let's assume that all those elements are 0, including so all blue elements are 0 and the red element is 0. So what does it mean? It means that this whole part of the column here will have zeros. So this is 0, this is 0, and so this is 0. This part here contains of all zeros. Well, what does that mean? That means that here this is column K. So we have, let's look at this matrix, and let's look at the columns of this matrix. This column K, and this is the column K minus 1. And the column K and the column K minus 1 go down up to row K minus 1. So this is where the red element is row K, and the row before is row K minus 1. So if we look at this part of our matrix, this submatrix, we will have in this submatrix that the first is some vector, and we cut it up to here. So what do we have? If we cut it up to here, we have vectors K minus in the dimension in R. Let's for a moment assume that we talk about matrix with real entries. So we have RK minus 1. All this, if we look at the vectors from here to here, the dimension is K minus 1. So we look at the vector columns. This is 1, 2, and so on, k. So we have k vectors of dimension k vectors in Rk minus 1. Because this is column k, and here the rows go up to k minus 1. So if we cut out the zeros here and we look at this lower and its upper left corner, we end up with this is the first vector, this is the second vector, and so on. This is the last vector in Rk minus 1, and there k. Well, if this is the case, we know that Rk minus 1 is a space of dimension k minus 1, and therefore these vectors have to be linearly dependent. And if these vectors have to be linearly dependent, if we continue with zeros further down, then we will also have a linearly dependent vector, which means that all these vectors from here to here, if we cut it now this way, so we extend the coordinates of these vectors down, so this will be linearly dependent vectors. But if these vectors are linearly dependent, that would mean that the determinant of the matrix AK is equal to 0, which would contradict to the assumption that the determinant of the matrix, the original matrix A, was different from 0, because we considered always matrices that are invertible. Therefore, if the pivot element is whatever we assumed is not correct, and therefore, so we ended up with a contradiction. Therefore, if the pivot element is equal to 0, there will be at least one element from the blue elements, from the blue entries, that will be different from 0. So if this is the case, we can exchange row k with any of these rows that are below it. However, we choose a particular row that we exchange it with, and this will be the row that has an entry that is the biggest in absolute value from all the entries, from all the blue entries. So how are we choosing here particularly? Is written, so if AKK is different from 0, so if the pivot element is different from 0, we continue as before with the Gauss elimination. If it is not, there is at least one J from k plus 1 to m, such that JK is different from 0, since A is invertible. We just discussed that. And then how do we choose from those elements the row that we want to exchange row k with? So this will be the row I, and this row will be chosen. So remember, here was A, K, K, K. And then below here, in this part, was A, K plus 1, K, K, and so on. These were all elements in this part of the kth column. So we choose an index I, for which the entry AIK has the biggest absolute value among all the entries that are in this part of the kth column, and in absolute value. And then we interchange row K and row I, and proceed with the Gauss elimination. This process is called partial pivoting. As a result, what do we get? If we start with the matrix A, and if the first element A111 is equal to 0, then we exchange row 1 with the row that has element that has the biggest absolute value among all the elements in this column, in column 1. And how do we do that? To do the interchanging of two rows of a matrix, we do this via permutation matrix. We just illustrated that. So as a result, we will end up with a matrix that has a pivot element different from 0. Then we apply the usual Gauss elimination. We know how to do that. We do that with the matrix L1. the first step of Gauss elimination, we end up with a matrix. If this matrix has a pivot element that is different from 0, then we continue, or we can do this even though it is different from 0. Even though it is different from 0, we still can do a pivoting. How can we do that? We can do it by multiplication with the matrix, permutation matrix P2. Now, if the element is different from 0, and we do not want to do any interchanging, then we can think of P2 as just the identity, nothing changes. Then we perform the next step of Gauss elimination, which is performed by multiplying the matrices, these matrices by a matrix L2, and so on. At the end, we finish with the last step of the Gauss elimination by multiplying by the matrix Lm-1. So this partial pivoting ends with representing this product, with writing this product, and at the end, this product will be equal to the matrix U. Note also that if partial pivoting is performed, that the entries of the matrix L in absolute value will be less than or equal to 1. Why? Because let's assume that this is the part of the kth column after partial pivoting. That means that here we put the element that has the maximum absolute value, and everywhere else would be elements which have absolute value less than or equal to the number here. There may be, sometimes 1 or 2 rows may satisfy this condition, then we choose just one of them. And then to compute the numbers L, we divide this number by this number, and so on. We divide this number by that number. And therefore, all the L JK numbers, which will be A, J, K, K, divided by A, K, 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 this is an absolute value bigger. The denominator is an absolute value bigger than or equal to the numerator, and therefore the absolute value of this will be less than or equal to 1. So let's go back and look at this product here, and we'll illustrate exactly what is happening if we have a 4x4 matrix, and a similar thing is happening for a general matrix, but we just don't want to get lost with in the dimension of the matrix. So if we have a 4x4 matrix, and let's PK, with PK denote the matrix that is doing the permutation that permutes row K and row I, and we said that every time that we need to do a permutation, then I is strictly bigger than K, because we permute this row K with a row I that stays somewhere below row K. So we have A, P1, L1, P2, and so on is equal to the identity. What is the idea? The idea is to collect all the P's in front of the matrix A, and this way we will end up with a P times the matrix A is equal to L times U. How do we do that? Let's consider a particular example. The matrix P2, let's say P2 is this matrix, and L1, so P2 and L1 is this matrix. We know that L1 is this matrix. So let's look at P2 times L1 and compute what is P2 times L1. P2 is obtained by the from the identity matrix. This is here row 1. This is row 4. This is row 3. and this is row 2. So this is how it is obtained from the identity matrix. If we multiply P2 times L1 on the left, then we will exchange the basically row 4 and row 2. This is what is going to happen. These two will exchange, row 2 and row 4 as a product, and this is what we see here. Row 4 comes on the place of row 2, and row 2 comes on the place of row 4. So what the claim is that if we take this matrix, which we denote by L1 tilde, so this matrix here is L1 tilde. So the product of P2 and L1 is the same as the product of L1 tilde and P2. Note that P2 and L1 do not commute. However, when you multiply P2 by L1, you will end up with a matrix. You can represent this product as a product of a matrix L1 tilde, not L1, but L1 tilde times P2, where L1 tilde has the same structure as the matrix L1. What does it mean, the same structure? It has ones on the main diagonal, 0 above the main diagonal, and probably non-zero on the first column, and here everywhere has 0. So you see here what is the L1 tilde. L1 tilde is like L1, but the only difference is that here this is taken from row 4, and here this number is taken from row 2. So it is interchanging, but not the whole rows, but interchanging the entries in the first column. So if this is the case, instead of P2L1, here we have P2L1, we can write it as L1 tilde P2. So we have L1 tilde P2. Therefore, the whole product can be rewritten as L1 tilde P2. This way, we moved P2 next to P1, before P1 here, but next to P1. So now we have P2, P1, and what we would like to do, we would like to move P3 next to these two matrices. So we want to have P3 moved, and what do we have? So we have L3. Now we have P3, P2. P3, P2 in the same way will be equal to some matrix L2 tilde times P3. And then we will have L3, L2 tilde, P3, L1 tilde. And now the same P3, L1 tilde. We want to move P3 in front of here P2. So P3 L1 tilde will be equal to L1 hat times P3. And therefore, at the end, what we will have that this matrix here as a product of permutation matrices is a permutation matrix P. So we have P times A is equal to, and then we will move all these matrices L, which we will discuss in a bit, on the other side by taking their inverses. So PA is equal to the product of the inverses of these matrices L. And as a result, we will end up that this is a matrix L times the matrix U. The important part that we noted here, that every time we exchange the position of the matrix P, of a matrix P with a matrix L, we will end up that this product will be some other matrix L times the same matrix P. But the important part is that this matrix L will have the same structure as the original matrix that we started with. And one can go through the same proofs, similar proofs as we did before, that because of this structure, the inverses of those hat and tilde matrices will be having the same structure as the inverses of the original L1, L2, and L3, and that when we multiply them, we will end up with a lower triangular matrix L. And therefore, we just illustrated that if we have matrix A, and we always claim that for every matrix A, there is a permutation matrix P such that PA is equal to L times U, where L is a lower triangular matrix and U is an upper triangular matrix. Here I just wrote the algorithm, which is the same as the Gauss elimination algorithm with added part that we interchange the rows. And how then we solve the system AX is equal to B. First, we look at the LU factorization for the matrix PA. We see that during the Gauss elimination, we also construct the matrix P. The matrix P, we see here that it is the product of all these permutation matrices. So P will be known, and L will be known, and U will be known. So if we start with a system AX is equal to B, we will multiply by P on both sides of the system. And then instead of PA, we write LU. And we need to solve this system, which we do this in the same similar way as before. We put UX is equal to Y. And therefore, first we solve LY is equal to PB, using the fact that L is a lower triangular matrix. And then we solve UX is equal to Y, using the fact that U is an upper triangular matrix, so the same as before. Now, sometimes what we did here so far was something called, and we said it, it's a partial pivoting. We are just interchanging row K at step K with one of the rows below that. What it can happen is that sometimes, however, it's rarely done because it is a lot of bookkeeping that needs to be performed. We can interchange also rows, columns, not only interchange rows, but interchange rows and columns. And to do an interchange of columns, as we discussed at the very beginning with the example that we had, we have to multiply on the right the matrix A by the permutation matrices Q1, Q2, and so on, Qm minus 1. And therefore, as a result, we see that the product of this permutation matrices is a permutation matrix Q. And as we discussed before, we bubble up all the P's, and we have that the their product will be a matrix P, and therefore we will have that P times A times Q is equal to L times U, and where P and Q are permutation matrices. Now, we actually saw that we started with system AX is equal to B, and we wanted to see how we solve this system. We know from courses in linear algebra that we actually look at the matrix, we look at the augmented matrix, and we perform the Gauss elimination. When we went into detail of how we perform the Gauss elimination, we discussed that we have the K, we ended up with the fact that we can represent the matrix A under special circumstances when AKK is different from 0 for OK, then we can represent the matrix A as a product of a lower triangular and upper triangular matrix. Now, this LU factorization of the matrix A, if it exists, can actually be done directly. And when we have this factorization, so when A is equal to L times U, and when the Li, the elements on the main diagonal of L are equal to 1, This is called Doolittle's method. When the upper triangular matrix is a matrix whose diagonal elements UII are equal to 1, this is called Kraut's method. And when the elements on the main diagonal of L are equal to the elements on the main diagonal of U, this is called the Cholesky method. So now we will see that the LU factorization in fact is not unique, and it will transpire in a minute why it is not unique. So let's say we start with a matrix A with entries Aij, and we would like to represent it as a product of this lower triangular matrix L and with this upper triangular matrix U. Without any Gauss elimination or anything, this is the main problem that we're trying to solve. We try to, so we know the A's, we know the original matrix A, and what we want to find the L's, the entries of the L, and we want to find the U's, which are the entries of U. What we're going to do, we're going to do the multiplication of the two matrices in a special order. So first, we know that to get this element A11, we have to multiply the first row of this matrix by the first column of this matrix. And because of all these zeros, we see that A11 is in fact equal to L11 times U11. So from here, we compute L11 and U11. And you see here that we have two unknowns, L11 and U11, but we have only one equation for these unknowns. And therefore, they are not uniquely determined. So either here we can put L11 to be 1, or we can put U11 to be 1, or we can solve it such that L11 is equal to U11, and then both of them will be equal to square root of A11. So you see here that this stage, and this will happen at every such stage, we will see how and when, but at least here L11 and U11 are not determined uniquely, because the relationship that they satisfy is only one relationship for the two unknowns. Then we go and we multiply the first row with all the columns. Why? Because all these zeros, when we multiply this row by all the columns, all these zeros will make all the elements that are from row 2 and below irrelevant, because they will annihilate these elements. And so then we will have that A1j, so the elements from this row are equal to the product of row 1 and the columns of U. So we have that A1j is equal to L11 times U1j. And therefore, since L11 has already been determined here, we can find U1j by this ratio. And of course, this could be done only if L11 is different from 0. Now, after this pass, we have determined all the elements of U from the first row of U, and the elements on the first row of L. Now, what we do is, so first row with all columns gives us the first row of U. If we do all rows times the first column, we do now all the rows. So this row times the first column, this row, the second row of L times the first column. And why do we do that? Because we want to take advantage of all the zeros below the U11. Because when we multiply any row from L by the first column of U, we actually will take into account only the first element in L, because all the rest will be 0. Therefore, we will have, once we do, let's say, ith row of L times the first column of U, we will have Li1. And then it will be equal to AI1. And therefore, all rows times the first column, all rows of L times the first column of U. We'll have AJ1 is equal to AJ1 times U11, but U11 has already been computed here, so we know U11, and therefore from here we will have LJ1. And again, this is provided that U11 is different from 0, which basically, as you see from here, is related to the fact that the pivot element here is the element A11 is different from 0. So as a result of this first pass, we know the first row of U and the first column of L, because we have LJ1 and we have U1J. So the first column of L is this is computed, and the first row of U is also computed. And then what we do, we go to the second column of L times the second column of U, because when we do that, this term here will be multiplied by this term here, and we already know it, it's from the red area. And then the only unknown will be L22 times U22. So if we do row 2 times row 2, second row times, so second row of L times second column of U, what I just discussed will be this one, and therefore we can have an expression for L22 and U22 because this will be already known. Now again, here you see that this is not uniquely determining L22 and U22, it determines their product, but we can distribute between quantities between L22 and U22. We can either enforce this to be 1, or we can enforce this to be 1, or we can do any distribution of the value of the product depending on what we are interested in. And in general, what is happening if you multiply, the general step is if you multiply row I and of L with column I of U, similar to what we have here, you will have that LII will be equal to the element on the main diagonal of the matrix A minus the product of the elements of the ith row of L and the ith column of U. And this will be known, and therefore we from here, not uniquely, will be determined LII and UII. And then if we continue further, we will determine through this formula the ith row of U. And also we will, the similar way as here, first we determine the first row of U. So we'll determine the ith row of U using that formula, and we will determine the ith column of L using this formula. So what is happening, we do several passes. So on the first pass, we determine these 2 elements. On the second pass, we determine the first row of U and the first column of L. Then the next pass, we determine these elements here and here. And then if we multiply the second row of L with each of the columns 3 and so on, we will determine these elements, the second row of U. And then if we multiply all the columns of L, actually from third below, from second below by all the by the second column here, then we will find the elements from the second column here in L. Because if we multiply L21 by L22, we know, but if we multiply L, let's say L31, L32 by this, then this will be already known times U12 will be known, but then we will have L32 times U22, and we will already know U22, so we will find L32, and the general formula will be this one. So this is a way to perform the LU factorization directly, not in conjunction with Gauss elimination. And what is happening is that there are some special matrices for which we will discuss. We discussed that before. Let's say last time we finished with a theorem like that we did not prove, but we just mentioned that if A is a matrix such that all submatrices which are on the upper left corner of dimension k times k from 1 to n, if they are all invertible, then A has LU factorization. That means in the Gauss elimination, you do not need to do pivoting. Now, what will happen is that we will discuss the several other matrices for which this is true. And we are going to use that types of matrices later. But the definition will be given now. So a matrix A is called strictly diagonally dominant matrix. It is square matrix. It's called strictly diagonally dominant if for every I we have this inequality. So what does this inequality mean? Let's say take the element, let's circle the elements on the main diagonal. So if we look at the first row, this means that the absolute value of the element on the first row that is on the main diagonal is strictly bigger than the sum of the elements of from this row of the main diagonal. So absolute value of A1, 2 plus and so on plus absolute value of A1n. If we look at the second row, this means that the element on the second row that is on the main diagonal, A22, so absolute value of A22 is strictly bigger than the sum of the absolute values of the elements that are on this row but are of the main diagonal. A21, absolute value of A21 plus absolute value of A23 plus and so on plus absolute value of A2n. And so on. This we do for every row. At the very last, the element absolute value of ANN is bigger than absolute value of AN1 plus absolute value of AN2 plus and so on plus absolute value of ANN minus 1. So if a matrix satisfies this condition, it is called a strictly diagonally dominant matrix. And for example, how can we check if a matrix is strictly diagonally dominant? Let's look as an example. Somehow this would mean that the mass of the entries is concentrated in the diagonal. So if I have, let's say, minus 6, 1, 0, 3, 5, 1, 4, 7, and 13. If I look at this, is it true that 6, because it is absolute value of minus 6, is bigger than 1 plus 0? Yes. Is it true that 5 is bigger than, let me put here minus, that 5 is bigger than 3 plus 1? Yes. Is it true that 13 is bigger than 4 plus 7? Yes. So this is strictly diagonally dominant matrix. What about the matrix minus 3, 1, 2, 3, 7, 0, 5, minus 1, 8. So this matrix will not be strictly diagonally dominant because from the even if we look at the first row, for example, we'll have absolute value of minus 3, which is 3. Is it true that 3 is bigger than 1 plus 2? This is not. We have to have strict inequality, and therefore this matrix is not a strictly diagonally dominant matrix. Now, what is the theorem? The theorem says that every strictly diagonally dominant matrix is non-singular And moreover, if we apply Gauss elimination for such matrices, this is separate, can be performed without pivoting. That means that we do not, that the matrix A, if it is strictly diagonally dominant, can be represented, can be written as a product of a matrix L and a matrix U. So to do the proof, this part of the proof is part of your homework. And now we'll do the first part of the proof. So let's say we have a matrix A that is strictly diagonally dominant, and we will show that this is a non-singular matrix. Assume the opposite. What does that mean? That means that if we look at the system AX is equal to 0, this system has solution, a vector X, which is a non-zero vector. And then we write the system. These are the equations of the system. This is the ith equation of the system. For I is equal from 1 to n, right? This means that the ith row of A is multiplied by the column vector X. And then what we do, this vector X, which is has components X1, X2, and so on, Xn, we know that this vector exists. We know that this vector transpose, we know that this vector exists. We know that this vector is non-zero. And then let's look at its coordinates. And let's choose an index k such that the kth coordinate xk of this vector is the maximum in absolute value. So let's choose an index k such that the absolute value of the kth coordinate is the maximum among all the absolute values. There may be more than one such index k, but nevertheless we choose one of them, and such an index will exist because the vector is a non-zero vector, so it has at least one non-zero component, and therefore such a k exists. And then if such k exists, then let's look at the kth equation here. This kth equation then will be in the form, let me write it here. The kth equation will be a k1 x1 plus a k1 x1 plus and so on plus a k k xk plus and so on plus a k n xn is equal to 0. This will be the kth equation. And then what we do, we leave this on the left hand side and we move the rest on the right, to the right of the equation. So we write AKK xk is equal to minus, and then this sum AKJ xj, when j is from 1 to n, but j is different from k because we left this term here. And then what we do, we look at the absolute values of both sides. So we put an absolute value here is equal to an absolute value here. Absolute value of the product is product of the absolute value. So the product of the absolute value is equal to this, which is equal to this, and we just use a triangle inequality. Absolute value of a sum is less than the sum of the absolute values. And absolute value of xj, because xk was the maximum of the absolute values of the components, so the absolute value of xj is less than or equal to the absolute value of xk. So if this is the case, we have this xk, and now xk can get out of the sum because it does not depend on j. The sum is over j, and this xk does not depend on j, so we pull it outside of the sum, and then we divide both sides of the inequality by absolute value of xk, which is strictly positive because, as I said, the vector is non-zero vector. And then what do we get? We get that AKK is less than or equal to the sum. So what does this mean? That the element, if we look at the kth row, AK1 and so on, AKK and so on, AKN of the matrix A, the element on the main diagonal, AKK in absolute value, is less than or equal to the sum of the absolute values of the elements of the main diagonal, and this is contradiction with the fact that the matrix is a strictly diagonally dominant matrix. Remember that the definition was strictly bigger than the sum. So therefore, this matrix is non-singular. As I said, the second part of this theorem is one of your homework problems. Now, another definition that we're going to use later too. A matrix A is called positive definite if x transpose times A times x is bigger than 0 for every x, vector x that is different from 0. Now, they're different in different books. This definition is different. Some books, in addition to that restriction, require that the matrix A is symmetric, and in some books they have only this definition. And I will explain to you, this is also somewhat associated to your homework, to a problem from your homework. I will explain to you why. So if we have a matrix A, no matter whether this matrix A is symmetric or non-symmetric, A1n, AN1, and so on, ANN, every matrix creates a quadratic form. What is the quadratic form? The quadratic form is this expression, x transpose times A times x. So if you look at the vector x, which will be the column vector x1 up to and so on xn. And if you indeed go ahead and compute what is x transpose times A times x, what is this? You see x transpose is a vector 1 times n is a matrix n times n, and x is a vector n times 1. So when you do the product, you'll end up with a number. And this number, in fact, can be computed in the following way. This is a sum. You look at the entries of the matrix, and every entry of the matrix has to participate in this sum. So if you look at the entry with indices I and j, that stays on ith row and jth column, so this entry will participate in the sum. And the index I, if you have index I, means that you will have to multiply this entry by xi. And the index j means that you will have to multiply this by the entry xj. And the sum is with respect to all the entries of the matrix A, which means with the sum is over all I and j from 1 to n. So why is this called a quadratic form? Because if you look at this, this is a function that is of the unknowns x1 to xn. So this is a function of n variables x1 to xn, and you see that all all the terms that participate in this sum are of degree 2. You have xi multiplied by xj. So these are the degree is 2, and therefore that's why it's called a quadratic form. So every matrix, no matter what, whether it's symmetric or not, is creating a quadratic form. And therefore, one can ask the question, is this quadratic form bigger than 0 for all x that are different from 0 or not? And if it is, as a function of x1 to xn, if it is strictly positive for all x's that are different from 0, then the matrix that created that quadratic form is called a positive definite matrix. Now, what is happening is that once you have the quadratic form, so you have your matrix A, the matrix A creates a quadratic form. You can go back and actually find a lot of matrices that have created this particular quadratic form. And among these matrices that created this particular quadratic form, there is a symmetric matrix that created this quadratic form. And then you may think that's why in some definitions they do not assume that the underlying matrix is a symmetric matrix. They just say to give the definition of positive definite, because they are just looking at the quadratic form as a function of x1 to xn, and they do not care where it came from. Because if you look at the quadratic form only as a function, as I said, you can find a matrix A sim that will have different entries than this matrix A. However, the quadratic form of this matrix A sim will be the same as the quadratic form of the matrix A, and the matrix A sim will be a symmetric matrix. And this is also a homework problem. Once you're given the quadratic form, how to create a symmetric matrix whose quadratic form is that given quadratic form. The next theorem tells us something about a symmetric matrix, that is Gauss elimination. The symmetric matrix A is positive definite if and only if Gauss elimination can be performed without pivoting, with all pivot elements positive. So this basically also tells you, as in the previous theorems, that then the matrix A will have LU factorization, not P times A will have LU factorization, but the matrix A itself will have an LU factorization. To go a little bit further, the following is true. A matrix A is a positive definite if and only if A can be factored in the form A is equal to L hat times D times L hat transpose, where L hat is a lower triangular matrix with 1 on its diagonal, D is a diagonal matrix with positive diagonal elements, and A is positive definite if and only if A can be factored in the form A is equal to L times L transpose. This is called Cholesky factorization, where L is a lower triangular matrix with non-zero diagonal elements. So here, when we talk about positive definite, we have the definition of symmetric. I will put here symmetric. You see here that if you are in this case, if you have this representation here and this representation here, in fact, there is a relation between this representation and this representation. If you look at the matrix D, then the matrix D can be represented as a product of these two matrices, square root of D and square root of D, where square root of D is a matrix where on the main diagonal you have the square roots of the D's. So here it is square root of D1 and so on, square root of Dn. So the product of the matrix square root of D by itself will give you the D1, the diagonal matrix D with D1, D2, and so on, Dn on the main diagonal. And the matrix L in the Cholesky factorization is actually equal to the matrix L hat here times the square root of D, where square root of d, as I said, is a diagonal matrix, where on the main diagonal you have square root of d1, square root of d2, and so on, square root of dn. Now, how do you do the algorithm for the Cholesky factorization? The algorithm for the Cholesky factorization, you do the following exactly. If you look at this algorithm here for the LU factorization that we had before, but instead of you put the transpose of L. So in this case, we will have L. So we will have L1, 1, 0, and so on, 0. Then we will have L2, 1, L2, 2, and so on, 0. So we will have that A is equal to Ln1, Ln2, Lnn, and then times the transpose of this, which will be L11, L21, and so on, Ln1, and then 0, and then we will have the transpose of, so you have the 0, and then L22, and then we will have the Ln2, and so on. At the end, we'll have 0, and we will have Lnn. So what is going to happen is that A has to be a product of these two matrices. So the first row of this matrix, the first column of this matrix became the first row of this. The second column of this matrix became the second row of this, and so on. And you see here, if we multiply the first row times the first column, we'll have L11 squared is equal to A11. So from here, we'll get that A11 is equal to square root of A11. By the way, again, as a part of your homework, you will have some additional properties for that you will have to write down for symmetric matrix. And this is one of the properties that A11 and all the elements on the main diagonal have to be positive. So this is well defined. And then if we go the first row with, now this way we will know this term. And now we multiply the first row with all the columns. So we will have L11 times, let's say, Lj, if you multiply by the jth column, it will be Lj1, because you won't have any more terms down because of the 0 here. The 0 will annihilate all the terms from the multiplication. Then it will be equal to A1j, because it is the first row and the jth column. So this will be known, and therefore you will have that Lj1 is equal to A1j divided by L11, and so on. So let's see, is the thing that we got. So we have L11 is equal to square root of A11, and then Lj1 is equal to AJ1 or 1J, because the matrix has to be symmetric. It is the same thing, whether it is J1. I think I put here 1J, but it doesn't matter. It's the same number because the matrix is symmetric. Where, yes, I have J1, but it is the same as 1J. So we end up with this equation for Lj1. And then if we look at the further for the we apply the algorithm for the LU factorization in this particular case, you will find what LII is. And this will be the expression for LII, and then you will find the expression for LJI for J, for the values of J from I plus 1 to N. And in the very end, you will compute the last term of the matrix, which is the A and the L and N term. So this is how you perform the Cholesky factorization. And once again, if the matrix A is a symmetric and positive definite, then this matrix can be written as a lower triangular matrix times a lower triangular matrix transpose. And sometimes, actually in a lot of cases, this Cholesky factorization is useful. And with this, we finish the Gauss elimination, and it is not really only Gauss elimination, because it is also related, or we discuss also factorization of matrices. We discussed the LU factorization of a matrix, or P times A, the LU factorization of the matrix P times A. We also discussed the Cholesky factorization for a symmetric positive definite matrix. So we covered that type of material. What I plan to do next is to go to iterative methods for solving linear systems. So the material is from the book, but it is not following the chapters as they are in the book. So far we discussed Gauss elimination for solving system of systems AX is equal to B when the determinant of the matrix A is different from 0. And we discussed that Gauss elimination is a direct method for solving these systems. There are other methods called iterative methods. In order to do iterative methods, we have to cover some preliminary material, which will enable us to know how to compare two vectors, in the sense how to measure distance between two vectors. And in order to do that, I have to cover norms and inner products. And this is a material which we'll cover in the next lecture. Once we cover that material, then we will go to iterative methods. And after iterative methods for solving linear systems, we will go to methods for solving nonlinear equations. And then we'll continue from there. But the part of linear algebra will be also iterative methods for solving systems. And we will talk about Jacobi, Gauss-Seidel, and the SOR method. Now let me see. I will start next time with scalar products and norms. And I want to just mention two things. Scalar products and norms are defined for general vector space. And they therefore include everything in its total generality. However, we will, during our course, we will discuss two types of vector spaces. We will discuss the vector spaces Rn, which is the, the vectors with let's say, vector columns with n coordinates x1, x2, and so on, xn. We will discuss the space of functions. Here we talk about L2, but later we'll talk about LP, which are the sets of all functions defined on an interval AB. Now we'll talk about one-dimensional functions. We're not going to talk about functions of more than one variable. We'll talk about functions that are defined on a finite interval. However, this can be done for infinite interval as well, doesn't matter. These are the set of all functions defined on an interval and taking complex values. They can take also real values, which are measurable, and such that the Lebesgue integral from a to b of absolute value of f of x squared dx is finite. Now, let me remind you that when we talk about the space L2, then the elements in the space L2 are not really functions. They are a family of functions or classes of functions, and we identify or we consider in one class all functions that are the same, that differ with each other only on a set of measure 0. So when we talk about functions in L2, we're talking about family or classes of functions that such that if you take two functions from the same class, the set of points at which they differ is a set of measure 0, which would mean that it's not the set in which they differ is not that it's not big. It's a set of measure 0. So this is another thing that I want to mention. But nevertheless, don't. This is more of an analysis or even at some point later functional analysis. So just think of the fact that this integral here, integral from a to b of f of x squared dx is less than infinity, and keep in mind that this integral is a Lebesgue integral. But we are not going to go too much into details into the Lebesgue measure theory or anything. It's just look at the definition and don't think too much about in whether it's Lebesgue integral or Riemann integral. It's a Lebesgue integral. Anyways, okay, so this is the end of lecture 3, and next time we will continue with scalar products and norms. The homework actually is only on covering the this lecture. The homework number 3 will be on scalar products and norms. Okay.